Now, I've presented pipelines as sort of what you need to do when the clock is running too fast for your logic to execute within a clock cycle. Pipelines are also providing the benefit of performance, right? You want to run your clock at a high frequency. So comparing, the essentially unpipelined computation versus the pipeline computation, the computation, the time between flip-flops is setting the frequency of our clock. So by pipelining our design, we're able to run at a higher clock. And that means instead of presenting, regardless of the way we structure our logic, we're able to present one new set of inputs every rising clock edge. So if we're able to run our clock faster, we're able to present more data and get a higher throughput through our circuit. All right, so I want to jump back now into MakerChip. So I've got loaded up here the Pythagoras' theorem example that we've seen already. And I just want to talk about the MakerChip platform, the waveform viewer, the diagram, how you correlate that with the code. Pipeline logic can be a little bit tricky to understand because it's distributed in time. So I guess I want to first just put everything in the same cycle, put everything in stage one of the pipeline. So you can see here everything is in the same stage. It's just combinational logic, computing Pythagoras' theorem, and we've just loaded in the waveform viewer. So we can pick a cycle here and look at the A and B values. So here I've got an A value of 9, I've got a B value of C, and remember in the waveform viewer the values are represented in hexadecimal. All right, so in hexadecimal a value of C is 12. So triangle that's 9 by 12 is resulting in a C distance of F. Okay. When I pipeline the design, we're distributing the computation in time. All right, so here's my new pipeline design and loading in the waveform viewer. Zooming in again, looks like we've got another C and 9 here. So now the C value is 2 stages later in the pipeline. Okay, and you can see here in the waveform that the A signals are tagged with an @1 because they're generated in stage 1 of the pipeline, and C is tagged with an @3 to let us know it's in stage 3 of the pipeline. And what we can understand from that is that there are 2 stages of flops, and that values that we're looking at for these stage 1 signals affect the stage 3 signal 2 cycles later. Right, and that's reflected in the waveform. We see the C value, the 9 value, and 2 cycles later, the F value on C. Right, this is the value that corresponds to these 2. And it can be tricky to line all this stuff up. It's easy to make alignment mistakes where you end up looking at the wrong value, say looking at this B instead, trying to figure out what's going on. So make sure you're paying attention to the timing that's marked on the signals. The waveform viewer in TL Verilog is just going to represent the signals at the time at which they were assigned. The waveform does load the system Verilog, all of the system Verilog signals for the simulation as well. And in an RTL sense, if we look at this A squared signal, for example, the A squared stage 1 and the A squared stage 2 are just 2 independent signals in an RTL point of view. The timing abstract modeling in TL Verilog sort of unifies those, so they're thought of as a single entity, a single pipe signal. But we can look at the signals at the system Verilog level, and you'll see there's a corresponding calc pipeline A signal in stage 1, and that one doesn't get staged, but A squared in stage 1 gets staged to stage 2. And you can see here the relationship pretty clearly. We've got this value of 10 here, and a cycle later, the stage 2 version has that value because we've gone through a flip-flop. All right, so just to kind of make sure the nature of this timing is clear. It can be useful to use the diagram to understand the logic and the flip-flops that you're implying in your design. So we just looked at an example of retiming, not exactly the same, but similar, more deeply pipelining the logic. And, you can see pretty clearly in the diagram the flip-flops that you're implying. Pretty simple when you're talking about a pipeline. We also looked at sequential logic, like the Fibonacci sequence, where we were feeding back the value, in the case of Fibonacci, with a 2-cycle feedback. If we put a similar feedback here, and I'm going to have to do at least 4 since my pipeline is 4 deep, let's do a value of 4 and build that. And you can see that this A signal, we're now feeding back both A, which is the short arrow, and the head by 4 version of A, which is the version of A that's been staged through the pipeline 4 times. You can see that feeding back into this expression. And we can have fun with this. We can refer to the version of A 12 cycles ahead, or 12, we can say 12 transactions through the pipeline ahead, 12 transactions ahead in the pipeline. So the A from 12 transactions ahead of us is the one that's gone through 12 stages worth of flip-flops and then gets fed back into this calculation. All right. So the diagram can be useful for understanding the logic that you're implying.